In these next couple of examples, we're going to review the five-step process on how to graph polynomial functions. We're going to do this by following the following steps. First, determining the end behavior using the leading coefficient test. Next, find the x-intercepts, and then find out the behavior of the x-intercepts. By that we mean if the graph touches or crosses at the 0. Next, we'll find the y-intercept. And then finally, using our number of turns rule, we'll sketch the graph. So our first one that we're going to talk about here is going to be the function x cubed plus 2x squared minus 4x minus 8. If we're going to talk about our leading coefficient test, that means our very first thing we have to do is find the degree of the function and the sign of leading coefficient. In this case, we know that the degree of this polynomial is going to be 3, which is odd, and the leading coefficient here is a positive 1. So since it's odd and positive, this means it will be a fall to the left and a rise to the right, like the normal s cubic. The next thing we want to do is find the actual zeros. In this case, to find the zeros, we're going to do this by setting the polynomial equal to 0, and then we can solve the polynomial by using factoring. In this case, since we have 4 terms, we can use grouping. So in the first 2, we can take out an x squared, leaving us with an x plus 2. And then on the second 2, we can take out a negative 4, leaving us with an x. Oh, in this case, made a mistake there. It should be an x plus 2. But our 2 factors are going to be x squared minus 4 and x plus 2. We can also note there, then we can further break down the x squared minus 4 by, since this was a difference of squares, into x minus 2 and x plus 2. This means we have 3 factors, which makes sense since our degree is 3. If we set each of these factors equal to 0, we're going to get an x equal to a positive 2, a negative 2, and then also another negative 2. So this means then, if we think about the behavior of these zeros, since there's only one positive 2, which is odd, it's going to cross at the x-axis. But since the negative 2 appears twice, giving us an even multiplicity, this means it's going to touch the x-axis. So if we go ahead and plot those at 2 and negative 2, we'll see here that we're going to touch at negative 2, but cross at positive 2. And we can go ahead and add in our end behavior, which we decided was falling to the left and rising to the right. If we look at our graph now, we'll note that the only thing we still need to figure out is what's going on between our 2 zeros. And we can do this by finding our y-intercept. Remember, to find the y-intercept, what we're going to do is plug in 0 for the x values. So this gives us 0 cubed plus 2 times 0 squared minus 4 times 0 minus 8. But if we simplify that, that's just going to give us negative 8. So our y-intercept here will be at 0, negative 8. Which in this case, we can go ahead and graph. And so if we go ahead and connect our points, we're going to get this lovely little polynomial graph here. And since this is a degree 3 polynomial, that means we can have at most 2 turns, which if we look at our graph, this has exactly 2 changes in direction, which means that we did graph it correctly. We can check our graph on Desmos by typing it in and making sure that our graph is close to what Desmos is telling us if we'd like to check that out. The next polynomial function we're going to look at is f of x equal to negative 2x to the 4th plus 2x cubed. We're going to start off again by doing the leading coefficient test. In this case, we're going to have a degree of 4, which is even, which means we're going to have the same end behavior, and then a leading coefficient of negative 2. In this case, then that means instead of being a rise-rise, that negative is going to make it flip over the x-axis, so this is going to be a fall-fall, or a negative infinity to positive infinity. The next thing we want to do is find the zeros. We're again going to find this by setting the polynomial equal to 0. If we look at this, we have a negative 2x cubed in both terms, so we can go ahead and take that out as the GCF. That would leave us with, in this case, an x minus 1. So we can set the x minus 1 equal to 0 and get out a positive 1. And we can set the negative 2x cubed equal to 0. But if we go ahead and divide by negative 2, that's still going to be 0. And if we go ahead and then cube root that, then that means we're going to get 0 3 different times, because each of those x's are going to be a 0. Since the x equal to 1 only appears once, then that's an odd multiplicity, so it's going to cross. But then same thing with 0, since it appears 3 times. still an odd multiplicity. So this means that at 0 and 1, we're going to be crossing. And we can go ahead and add in our end behavior, which will be a fall. So in this case, the only part of the graph that we're missing information about is in between 0 and 1. Now, if we know here, though, we actually already have a y-intercept of 0. So what we're going to do here is use our intermediate value theorem to find a different point to help us. So we need to pick an x value that's between 0 and 1. In this case, let's go ahead and find another point to use. In this case, let's go ahead and try x equal to 1/2. This is a nice easy point to use. So we're going to plug in 1/2 for our x values, which gives us -2 to 1/2 to the 4th power, plus 2 times 1/2 cubed. And if we type that into our calculator and simplify, we're going to get out a y value of 1/8. So that means here that our point at 1/2 is going to be 1/2, 1/8. And so we can go ahead and graph that, giving us this little M-shaped graph here. Which again, if we want to go ahead and think about this, since we know that we're going to have at most 3 turns on our graph based on the degree of 4, then we can go ahead and assume that our graph kind of looks like this. Again, we can check our graph by using our graphing calculator or Desmos to see if our work is correct. Our next polynomial we're going to look at is x to the 4th minus 6x cubed plus 9x squared. Using the leading coefficient test, we again have an even degree, because it's 4, with the leading coefficient of +1. Since it is even, that means it's going to do the same behavior, and since it's a positive, this is going to be a rise, or a positive infinity. Next thing we want to do is look at try to find our zeros. Again, we're going to set that equation equal to 0. And if we look at this guy, we notice that we have an x squared in all 3 terms. So if we go ahead and GCF out an x squared, that's going to leave us with an x squared minus 6x plus 9. But if we look closer at that leftover quadratic, that is a trinomial that we can use our AC method on, our cross method, and think about what would multiply to +9 and add to -6. Well, in this case, that would be -3 and -3, which if we also use our special cases of perfect square trinomials, we could also use that as well. But we'll get the 2 factors of x minus 3, x minus 3. And so if we go ahead and set these equal to 0, we're going to get x equal to 0 and 0 from the x squared, and then x equal to a +3, and then also another +3. So since 0 and 3 both appear twice with even multiplicity, then that means on the x-axis that our graph is going to touch at both of those zeros. So at 0 and 3, we're getting this touch. And we can go ahead and draw in our end behavior because it's going to be a positive. Sorry, I forgot the word for end behavior there. The next thing we want to do here then is find out what's happening between 0 and 3 on our graph. Again, just like last time, we already found our y-intercept at 0. So we're going to use another point to try to find the behavior of our graph. So we could choose any value we want between 0 and 3, but I would recommend choosing a nice easy one. So like a nice one we could use 1 or 2. So I'm going to use 1. So if we plug in 1, we're going to get 1 to the 4th minus 6 times 1 cubed plus 9 times 1 squared. And if we go ahead and simplify that, then we get out a y value. We're going to take that 1 minus 6 plus 9, get a y value of 4. So that means at 1, our y value is 4. So we can go ahead and graph that, giving us this W shape right here. Again, since we have a degree 4 polynomial, this means that we're going to have at least 3 turns. And so this graph does match our number of turns properties. Again, we could check our work on a graphing calculator or Desmos. Please pause here and go back to any of these examples if needed. But these 3 examples here are going to show us how to graph polynomials using all the properties that we've learned from our equation. Please go back and review as needed.